A right circular cylinder can be made of metal. Right circular cylinder a right circular right cylinder can made of metal needs to be constructed to hold 350 cubic centimeters of volume. Find the dimensions of the right cylinder metal can that will minimize the cost of production. So that makes sense. So it's like a soda can, right? When they make soda cans, they have to hold a certain amount. I think that's might be similar to how much I can't remember honestly. Like I know it's 12 milliliters a soda can usually. I don't know how many cubic centimeters that is, but let's say it's about like a soda can. They got to hold a certain amount. What size should they make the can? Right, because you can make the cylinder like really narrow and tall, and it'll hold all that soda, or you can make it almost like a tuna can, kind of wide and flat, or more in the middle. What shape will minimize the cost of production, least amount of material to hold that volume of liquid or whatever's inside? All right. So how are we going to do it? Well, they give us the formulas in case we don't know those. Volume, area of the sides, and the area of the top and the bottom circles, pi r squared. It says the formula for the total surface area, top circle, bottom circle, and sides of the right circular cylinder in terms of R only, not H, is. So how do we find that? Oh no, I'm sorry. So they're giving us that. So this is yeah. So on another problem, we will find that formula. Here they're just giving it to us. And now we're gonna conclude this problem. We say, okay, use that formula now. So how we find that? That's another problem, the setup. So once you have that, we're going to conclude it on this part. To minimize the cost of production, minimize the metal surface area. The radius of the metal should be, so we got to find the R. So okay, let's take that S equation. I'm going to write it out up here. 2 pi r squared plus, I'm going to simplify here. Pi cancels pi. R cancels one of those R's. 2 times 350 is 700 R to the minus 1 because we only have one R left on the bottom, right? So it's R to the minus 1. Okay, now how do we minimize the cost or the metal surface area? You take the derivative. So bring that 2 down. So that'll be 4 pi R to the first power minus 700. Bring that down, subtract 1, R to the minus 2. And then you set it equal to 0, right? You know how to find how to maximize or minimize that. We take the derivative, set it equal to 0, because when the derivative is flat, when the derivative is 0, that's our peaks and our valleys, highs and lows. Okay, let's jump this to the other side. So we get 4 pi R is positive 700. I'm going to move that R to the bottom because negative powers jump to the bottom. And now I'm going to multiply both sides here. Let me multiply by R squared over 1. Let's kind of scribble it there. Both sides. Boom. So that's going to be 4 pi R cubed is 700. All right, let's keep solving for R. Divide by 4 pi. Boom, boom. R cubed. 700 over 4 pi. How do we finish getting R alone? 1/3 or cube root. Same thing. 1/3 power cube root. Cancels R's alone. We'll go to Desmos. 700 over 4 pi to the 1/3. 700 over 4 pi to the 1/3. 700 over 4 pi. So I'm going to go parentheses. 100 over 4 to the power 1/3. There we go. 3.8191. 3.8191. There we go. That's the radius. So that's how you should make that can. That's the radius that'll minimize the cost, the least amount of material on the outside to still hold that volume you need. It's a very practical question for people to make containers big and small, is how do we make it hold what we need to hold and use the least material possible? That's the radius you should choose to make the least material possible. And so there we go.